Okay, so hi to everyone. My name is Francesco Capozzi, and I am currently a postdoc at the Max Planck Institute for Physics in Munich. And today I'm going to discuss a recent paper I've done in collaboration with Georg Raffelt. And in this paper, we are basically updating the bounds on some non-standard neutrino properties that are given by red giant stars. So before starting, so in order to understand how we can get bounds on axions using red giant stars, let's look at the color magnitude diagram, which is most likely a plot you have already seen before. So on the y-axis, we have luminosity of a star, which is increasing going upwards. Then on the x-axis, we have the temperature, which is increasing going on the left. And each of these black dots is basically a star. So you can see that, you know, the stars, they are more or less clustering where on the main sequence where they spend most of their life. Then if we move to the top right corner, we start having the red giant the red giant branch, which is exactly what we will be focusing here in this talk. Now, the most important thing we need to know in order to understand this axion bound is the tip of the red giant. So the tip is basically the red giant star with the maximum luminosity, which, at least as an example in this plot, is given by this red circle in the top right corner. So basically a red giant star during its life is moving from the bottom left, more or less starting from the main sequence, is moving upwards towards the top right corner, and then it reaches this tip, which is the moment where it has the maximum luminosity. Now, if we add some extra cooling to a star, which might come from axions or neutrinos having some non-standard properties like an anomalous dipole moment, then something changes in the star, and in particular regarding the tip becomes more luminous. So this means that if we compare our theoretical predictions on the luminosity of the tip of the red giant given in the standard model with our observation, if there is some sort of disagreement, this might be a hint in favor of the existence of some extra cooling, which might come from different sources. Now, why do we want to update the constraints coming from the tip of the red giant? I mean, this is a very old topic. People have been focusing on this maybe starting from 30, 40. So why doing an update now? So there are three main reasons for doing that. The first one is that usually these bounds are coming from red giant stars in globular clusters. And the main uncertainties of these bounds, they come from the distances. Basically because what you measure is the apparent magnitude. But in order to get a bound, you need the absolute magnitude. But to get the absolute magnitude, first you need, of course, the distance, or the distance modulus, which is more or less the same thing. And the relation between the absolute and apparent magnitude is given by this formula, this very simple formula here. So until now, the most important uncertainty was coming from the distance. However, very recently, there has been a reevaluation of the distances of the globular clusters using some inputs coming from the Gaia data release 2. Basically, Gaia is doing a very nice job in measuring the proper motions of stars. Proper motion is basically the angular variation of the position of an object with respect to the background. And if you know very well the proper motion, and you know very well also the tangential velocity, which comes from a different kind of measurement, you can also get the distance, because there is a proportionality relation between these quantities. And so using these inputs, you can get a very precise measurement of the distances. Another reason why we want to update these bounds is the following. So As I told you before, people have mostly focused on the globular clusters, but red giants, they are present also in other galaxies, like for instance, the large Magellanic Cloud. This plot is showing the color magnitude diagram for the large Magellanic Cloud, where you can see that this this black band going to the top right corner is exactly the red giant branch stars. And you can see that there is a line, an horizontal line, a black line, which is basically indicating the tip of the red giant line, which in this band, because here they are focusing on the infrared band, basically the tip of the red giant line is horizontal, which means that there is no dependence on the luminosity with respect to the temperature. And so in principle, one can use also red giant stars coming from other galaxies in order to get bounds on axion. And this has never been done. However, the calibration of the tip of the red giant using other galaxies, like in this case, the Large Magellanic Cloud, has been done for actually a completely different reason. And that is to move upward in the cosmic ladder. So basically, you start by calibrating the tip of the red giant in the Large Magellanic Cloud. Then you use red giant stars in further galaxies to calibrate supernova 1A. And once you have this calibration, you can move even further in distance by just using supernova 1A. And in the end, you get a very nice measurement of the Hubble constant. So in principle, there is also this very nice relation between tip of the red giant and the Hubble constant. And I'm going to say something more about this later. Then we have a third reason to update these bounds, and this is mostly theoretical. So, of course, we have had some improvement in terms of distances. So this is all observational, but there is also some improvement in the theory. In particular, there has been a very recent paper by Serenelli et al. In 2017 in which they provided a very nice theoretical calibration of the tip of the red giant, which is given by this formula, which is given the absolute magnitude of the tip of the red giant as a function of the temperature or color index. They are more or less the same thing in the infrared band. And moreover, in this paper, they also give a very thorough assessment of the theoretical uncertainties connected to all the inputs you have in the theoretical models for star evolution. And so the uncertainties are a very nice, a very important input to calculate in the end the bounds. Now, let's have a look on the current calibrations we have. So this plot is basically showing the error bands for the empirical calibration on the top and theoretical calibration at the bottom. But we start from the empirical calibrations. The little circle in between these bands is basically the best fit point. So now these gray bands here, they are the old calibrations for the globular clusters M5 and Omega Centauri, whereas the colored one just below them, it's our new calibrations, where basically the only change we have applied is by introducing the new distances given by, the new inputs given by Gaia. And you can see that there is quite a significant improvement. Now, these other bands I'm showing here, they are not globular clusters, but here we are talking about other galaxies. In particular, you have the Large Magellanic Cloud, or you have the small Magellanic Cloud, but the most precise one is actually the LMC. However, for the LMC, we have two bands, one coming from the Friedman et al. Group, and the other one is coming from Adam Rees et al. Group. Now here, the one in gray is the one from Adam Rees et al. We are not using that just because the Friedman et al. One is providing a more conservative bounds on the extra cooling. That's it. Now, another significant point is that, you can start from the tip of the red giant, and then you can move up in the cosmic ladder and reach the Hubble constant. But in principle, why can't you do the opposite? So you start from the Hubble constant given by a different measurement, for instance, the one coming from CMB, so basically Planck, and then you go down the cosmic ladder and you reach a calibration of the tip of the red giant. And this is basically what we have done in this last bar, in the empirical calibrations, where we have inverted the LMC calibrations, and we have put as input the H0 value coming from Planck, and we have obtained a calibration for the tip of the red giant. And you can see there is, in the end, a good agreement among all the empirical calibrations. Now, if you think in terms of Hubble tension, I mean, this plot is showing that in principle, if you just focus on this plot, there shouldn't be any Hubble tension, but we are not putting any emphasis on this point because this is, of course, a very delicate debate going on concerning the Hubble tension. This is why in the title of our paper we didn't put any, there is no Hubble tension, because we are still kind of investigating in this. But it's strange, according to us, that if you calibrate the supernova 1A with Cepheid stars, starting from the large Magellanic Cloud, you get a value of H0, which is completely different if you start from TRGBs, from the tip of the red giant, again, starting from the large Magellanic Cloud, and then you move up the cosmic ladder, and you get a different value from the Hubble constant. This is very strange. So this is a topic separate from axions, but it's something that we need to investigate more. Now, in terms of theoretical calibrations, we have considering two of them. One, it's from this V13 paper. It's basically this Vio et al. Paper from 2013. So the gray band is the old theoretical calibration that we have updated, because very recently in this paper I was telling you about, this Serenelli et al., they have pointed out that Vio et al., they shouldn't have used in their theoretical calculations the weak nuclear screening for the calculation of the nuclear reactions happening inside the star. They should have used instead the intermediate prescription for the nuclear screening. And they have also estimated that using the intermediate screening, there is going to be a shift of the tip of the red giant towards higher luminosities of about 0.09 magnitude, which is exactly why you see a shift between the upper and lower band that you see below. And finally, we have the Serenelli et al. Theoretical calibration, which is very well consistent with the Vio et al. Ones. The only difference is that there is a different philosophy of errors. Serenelli et al., they only quote errors in terms of maximum error, so you have to maybe intend them in terms of a top hat function. Whereas Vio et al., they usually use, the root mean square error. So, usually 1 to sigma error band. A very significant point I want to say is that if you compare empirical and theoretical calibration now, since the distances have been updated, there is no longer the dominance of observational error, but now the theoretical errors are the one dominating. And this is quite a significant shift in terms of trend. Now, let's get these axion bounds. Here we express the bounds in terms of G13, which is just, the coupling to electrons multiplied by 10 to the 13. And we are considering the theoretical prediction for a color index or temperature of about 1.8, which is exactly the temperature or color index for the Large Magellanic Cloud, for the tip of the red giant of the Large Magellanic Cloud, and also very, very close to the globular clusters we are considering. Of course, the theoretical predictions, they are going to be shifted when you include extra cooling, and Vio et al., they have provided the the calculation of this shift in terms of G13. And so you can see this delta M is basically this shift introduced, this shift in terms of luminosity or magnitude of the tip of the red giant. And you can see the dependence of delta M as a function of G13 in the second equation, whereas the sigma is just the error on the theoretical prediction, which of course has also a dependence on G13, whereas the other two contribution, one comes from just the theoretical input and the other is the bolometric correction, where the bolometric correction is just something you need to add to the theoretical prediction to obtain the magnitude of the tip of the red giant in the band you are actually comparing with the empirical ones. And in this case, it's the infrared band. Then you need to apply a comparison with the empirical calibrations, and we do that by just assuming Gaussian errors, and where the total error is just the sum in quadrature of the error of the empirical calibration, which is not the one dominating again, plus the error on the theoretical calibration, and then you just you integrate this likelihood function up to 68 or 90% confidence level. And if you use the empirical calibration coming from the large Magellanic Cloud, you get a bound on G13, an upper bound of 0.82 or 1.6 at 68 and 90% confidence level. If you compare with the previous bound coming from Vio et al. Of 2013, there is a factor of 3 of improvement, but more or less, I mean, in 30 years, this bound, they have not changed that much. They're mostly been in the same ballpark, which means that our understanding of the theoretical calculation of stellar evolution, they've always been quite consistent with the observations. In conclusions, so now with the new distances for globular clusters and also for the large Magellanic Cloud, basically the bounds now are for axions, but also for neutrino non-standard properties. I've not reported numbers, but I mean, the thinking is basically identical. Now the errors are dominated by theory. Now, extragalactic calibration, they actually provide a very competitive bounds with respect to the one given by globular clusters, and this is a new result, which I think should be pursued also in the future. In principle, having a compound of globular cluster can provide further info and, of course, stronger constraints, but you need to be careful when you have to take into account errors, because some errors between different globular clusters can be correlated. So doing that, of course, you can do that, but it's much more complicated. And also the connection of the tip of the red giant with the abort tension or the H0 in general needs. And I think this connection is quite nice. At least I find it very interesting. And yeah, this is it. Thank you all.